Hello everybody. In this video, we are going to be dealing with the nature of roots as well as the discriminant. So we are first going to be talking about what is the nature of roots? What are roots? And why are we discovering their nature? So for this first example, notice that we are given some quadratic, well, I wouldn't really call it a quadratic equation because clearly if you multiply it out, you're going to get a polynomial of a fourth degree at its highest. But what do you notice? We have a quadratic equation here in this bracket and a quadratic here, meaning we can factorize and find the roots. So when we solve for x in these types of equations, we call them the roots. All the x values that we solve for are roots. And the nature is essentially what is being asked in these questions. Are they integers, which is the set over here? Are they real numbers? Are they rational values or irrational, with the apostrophe meaning not rational? Okay. So let's just try and solve the question, and then you'll get an idea of what nature of roots really is. We want to find the roots of the equation, which are the x values, and we want to determine what is their nature. Meaning we need to identify whether they're either one of these categories. Okay, so when we look at this equation here, we have x squared minus 5, and notice that the only best thing that we can really do is a difference of two squares. But before we do get further into this, well, I guess, you know what, we can go straight into looking at this equation. It's fine. This is a difference of two squares, okay? So we can do it like this. We can write it as x minus the square root of 5 multiplied by x plus the square root of 5, okay, which is equal to 0. One thing that we can do is we can work with the brackets one by one, okay, because notice what I'm doing is I'm taking x squared minus 5 and equating it to 0, then we can take this and then equate it to 0. But how do we notate that? Well, if you want to notate it in that way, okay, you can say or, and then you deal with it from there, right? Then we're going to take the other one, which is 2x squared plus 3x minus 2 equals to 0, okay? You can also do that. So notice that if you factorize this part over here, what we are going to get is 2x minus 1, if you use the grouping method or whatever method you'd like to use, and then we have multiplied by x plus 2, okay, and this is equal to 0. Don't forget the or. And then here, we already have our values. And remember, each bracket needs to be set equal to 0 in order to find our roots. So for this side, we can say that x is equal to square root of 5, or let's do it one by one like this. X minus square root of 5 is equal to 0, or x plus square root of 5 is equal to 0. Notice that I let both brackets be equal to 0 for the first one here. And then for this part here, we are going to say or 2x minus 1 is equal to 0, or x plus 2 is equal to 0. Okay. Now, before we solve these roots, I want you to understand something, right? The method that I took for the difference of two squares was I forced 5 to be broken up into square root 5 times square root 5. Right? Because if you multiply square root 5 by square root 5, you get 5. Or if you square the square root of 5, you get 5. Meaning you can write square root of 5 as, or I guess you can write 5 as a perfect square by taking the square root of 5 and squaring it. Okay. And then you can break it up like this using dots, or difference of two squares. And you can use a grouping method in order to get to this point over here, which I've covered in one of my previous videos. Okay. Otherwise, you could also do it all in one. So meaning you don't have to say or, because or is just the notation. You can literally just put all the brackets right before the equal to 0, and then you can do it straight towards this point. Either method works. And then we just solve for x individually here. X is equal to square root of 5 for this one, or x is equal to negative square root of 5 for this one, or this should be x is equal to a half if you were to take the 1 over and then divide both sides by 2, or x is equal to negative 2. Okay, cool. Now we found our roots. So this over here, I'm going to indicate here, this is our roots. Now we need to determine the nature of these roots by answering these questions here. Number A says where x is an element of integers. Now what are integers? Integers are basically whole numbers that are able to go towards the negative values. So things such as maybe negative 2, negative 1, 0, 1, 2, all of those values, but nothing in between, okay? Those are integers. So what values describe what integers are? Well, if we look at the square root of 5, it cannot be an integer because it's a square root value, okay? It is not a whole number. So with negative square root of 5, it's also not an integer. A half is not an integer, however, it is a fraction. We can't let it be an integer. So the only one that we can see that is an integer is negative 2, because it is a whole number and it's negative. Okay, so therefore the only value that can be an integer is negative 2. We can say x equals negative 2. Okay, that's the root that can be an integer. What's the next one? The next one is x is the element of real numbers, meaning it has to be real. And when we're saying non-real, by the way, meaning r, non-real is when we have an apostrophe by the r, but otherwise here, x element of real numbers, it has to exist. And if it doesn't exist, it's undefined. So square root 5 is a real number. Negative square root 5 is also a real number, it exists. 1 over 2 is also real, and negative 2 is also real. So the non-real values are just imaginary numbers, like with complex numbers, and undefined values or indeterminate values, all of those things that don't exist in the real number system. So basically all of them, x equals to negative root, let's say plus minus root 5 just to make it quicker. We also have x equals to a half, and we also have x equals to negative 2. Those are all those values, okay? So here, the next one, number C, is rational numbers, meaning they can't have an infinite decimal, right? So rational numbers can be written as whole numbers, integers, so every single number except an irrational and a non-real, okay? So square root of 5, if you put it on the calculator, it'll have a decimal that goes on forever, meaning it's not rational. So we can't use root 5. Same with negative root 5. It's the same thing but negative. So we can't use that either. Half can actually be rational. Why? Because it's written as a fraction, and it's 0.5 if you look at it in the numerical version, right? The decimal form. It's 0.5. It has an end with a decimal, so which means it is rational. And we can use that. And negative 2, well, yes, we can write it as a fraction, which is negative 2 over 1. And yes, it's not an infinite decimal, and it's real. So meaning the values that are real, or sorry, not real, rational, is x equals a half, and x equals negative 2. And then number D is going to be irrational, right? Meaning the decimal doesn't have an end, okay? Notice that that is basically going to be everything that we have that is not rational, which is square root of 5 and negative square root of 5. So it's x equals plus or minus square root of 5. Okay, so we can write it like that. So this is the nature part, okay? So we understood the nature from those roots. Now let's get into the discriminant by using nature of roots. Okay. So now we have to deal with the discriminant, okay? So this is our quadratic equation, or our quadratic formula. Sorry. So our quadratic formula is this, okay? Everything looks alright. But the discriminant is essentially us just investigating, discovering the square root, the inside of the square root. Because remember, what do we know about square roots? Square root values have to be positive or equal to 0, right? In order to be real. If you have a negative value inside of a square root, it is complex. It is not real. Imaginary. Okay? So, meaning what we want to do is we want to determine what is the nature of the roots by using the quadratic formula. And that is what the discriminant is. Okay, and what is the equation that we use? Well, the discriminant we denote by using capital delta, right? The triangle. And this is equal to the inside of our square root, which is b squared minus 4ac. Remember what I said? We are investigating the behavior of the inside of the square root, and if we can see that that this whole discriminant, the whole value is a negative value, then it's now complex. But if it's also positive, then we need to have some type of behavior with the roots. And I'll tell you about it now, okay? So this is going to be our conditions for the discriminant, okay? So if the discriminant, in this case here, is less than 0, meaning it is negative. If it is less than 0, then this indicates to us that the roots that we get are non-real. So they're not real. Meaning there will be non-real numbers. Okay? What if the discriminant is equal to 0 though? What would happen? Well, you kind of need to know that there will be two roots, okay? And they are equal to each other. They will be equal to each other because this whole thing is just 0, okay? Because look here, think about this, right? If you have the value of 0 in the square root goes away, and you're just going to have the same value for the roots, okay? So there are two roots, and then they are equal, and they have to be rational. Because it's not going to give us that square root anymore. The square root is gone. But what if the discriminant is greater than 0? Now there are two conditions, so I'm going to write both of them down. So the first condition is if it is a perfect square, okay? And then the second one is not perfect square. Okay, I'm going to just draw a square. So if it is a perfect square, it has two roots, okay? They are unequal, however, because it's not equal to 0. If it's not equal to 0, then it will be unequal roots, okay, if it's greater than 0. So it's unequal. However, because it's perfect square, right, we should get something more neat, which means it is rational. That's the nature of the roots. And then if it's not a perfect square, we still have two roots, and it's still unequal to each other because they give different values since the square root exists. However, because the square root exists, it's usually just irrational. Okay, that's the nature of the roots. So you need to divide it into subcategories. You need to notice that if the discriminant is less than 0, it's negative, meaning it's imaginary, it's not real, it doesn't exist, okay? If it's equal to 0, you get two roots, but however, it will be equal to each other, and it'll be rational, okay? Because the square root is gone, and then if the discriminant is positive for the perfect square, two roots, unequal, rational, and then if it's positive with non-perfect square, then it will still have two roots and also be unequal. However, it is irrational. Okay, because if it's not a perfect square, it's going to be messy. Okay, because the square root doesn't cancel out the square, by the way, just in case you wanted to know. So you might get a square root of 5 incident like we did in the last example. So let's do example to see what happens from here. How do we use the discriminant? Okay, so here's our example, right? We have 2 of them, but let's look at the question. It says determine the nature of roots of the following equations without solving them. So in this case over here, we need to determine the nature of the roots and we need to not solve them. But we're going to use discriminants for these types of questions. So the first question says a, which is 4x squared plus 12x plus 9 equals 0. So these are super easy. Okay, so we have a quadratic equation form over here. It's equal to 0. That's perfect, okay? Meaning we can just solve for the roots. Well, not really solve for the roots, but we need to make sure that 0 is on the other side in order to actually use this discriminant, right? Because we need to set it up for the quadratic formula, if you understand what I'm saying. Because now we have a quadratic form with ax squared plus bx plus c is equal to 0. And now we can use the discriminant, okay? So number A is the first thing we have to do, by the way, is say capital delta is equal to 4, or sorry, not 4, it's b squared minus 4ac, okay? B squared minus 4ac, that is what we have, okay? What is our b value, though? Our b value is the 12, right? So remember, this is A, this is B, and this is C. B is positive 12. So what we are going to have is we are going to have positive 12 squared minus 4 into A, which is 4, and C, which is 9. Okay. Then we just solve for delta. 12 squared is 144 minus 4 times 4, which is just equal to 64, and 64 times 9, you can just put everything in a calculator, just make life much more easier. So once you put everything in the calculator, notice that you'll get a value of 0, okay? And what we say about 0, we said that if the discriminant is 0, then it will have 2 roots, they are both equal, and it will have rational roots. So that's what we're going to say. Okay, so when we're answering the question, we're determining the nature of roots. So therefore, we'll say that the roots are real. Okay, they're equal and rational. So that's how we're actually going to answer the question. If it's anything similar that has all these key points saying that roots, remember the plural, that are real, equal, and rational. Okay, it has to have those 3 key points. Then number B, which is the last one, is negative 2x squared minus 4x plus 4, okay, is equal to negative 2. Now notice that this is not in proper quadratic form. Why? Because clearly there's a negative 2 on the other side instead of 0 like the other one. So we need to make sure that we take the negative 2 over by adding both sides by 2. So then what we're going to get is negative 2x squared minus 4x plus 6 equals to 0. If we add both sides by 2, we're going to get that, okay? Alright, and now we can use the discriminant feature that we have, okay? So the discriminant is equal to, what is it? B squared minus 4ac. That's all you do. And then you just substitute from here. We know that b is equal to negative 4, okay? So it's negative 4 squared minus 4 into negative 2 multiplied by c, which is 6. It is not positive 4, by the way, because we have to get that constant, and it has to be equal to 0 in order to get that full constant, and we can use the quadratic equation properly. So it is 6. Okay. And then here, our discriminant, the value that we should get from this discriminant is going to be 64 if you plug it into your calculator. And notice that this value is greater than 0, meaning the discriminant, or you can even say over here, the discriminant is greater than 0. It is positive, okay? However, is it a perfect square or is it not a perfect square? Because there's two conditions. Because it's a perfect square, it's 64, that's 8 times 8. Because it's a perfect square, we say here, once again, roots are real. Okay? However, they are not equal. Remember, they are unequal roots because the discriminant is greater than 0. And because it's a perfect square, it will be rational. If it was not a perfect square, it would be irrational. And by the way, in a case where the discriminant is non-real, meaning it's negative, then you will just say roots are non-real. That's all. Remember, that was the only description we gave it. Okay. Otherwise, that is what discriminant is, and that is the nature of roots. We are just trying to investigate the nature behind the roots that we have discovered, which are the x values. Okay.